Good morning, everyone. My name is Chongdan Li. The topic of today's presentation is network embedding operations preserving insufficiency of linear codes. This is a co-work with my advisors Stephen Weber and John Walsh. At first, I would like to take this opportunity to advertise our related work in recent submission to Transactions on Information Theory, which is also available in arXiv. In that journal paper, we presented the rate regions for 7,369 isomorphic networks, which represent more than 0.1 million networks. Here, the non-isomorphic means symmetries or permutations are removed, and we developed the algorithm and software can be used to calculate these rate regions rather than write down the expressions by hand. So we also consider the sufficiency of simple linear codes, say binary codes. We say FQ codes suffice for a network. We mean that for every extreme ray of the rate region, which is usually a cone with the dimensions of capacities and source entropies, it can be achieved by FQ codes. As shown in the picture, C1, C2, and C3 are basic codes associated with the extreme rays. And then for an arbitrary point C in the region, we can construct the code to achieve it according to the conic combination. Even though we have computation tools to compute the rate regions and check the sufficiency of simple linear codes, we still cannot handle large networks due to the computation limit. This forces us to address this problem with another perspective, and we got inspired from matroid theory, where the linear representable matroids are usually characterized by forbidden minors. For example, U24 is the forbidden minor for binary matroids. Like it shows in the picture, larger matroids on larger ground size are extensions of matroids with smaller ground size. For those not FQ representable matroids, the red circles here, their extensions are not FQ representable either. So we want to see if networks have similar characterization. So if so, we could have a list of forbidden embedded networks for sufficiency of linear codes over a field. So like the picture shows, if a big and a complicated network is not FQ code sufficient, can we find the smallest embedded network that FQ codes are not sufficient? This work tries to define some network operations to obtain embedded networks, preserving the sufficiency so that if a big network is good, the embedded networks are also good. Equivalently, if a small network is bad, its extensions will also be bad. And we've defined 3 operations and consider the scalar binary codes for a special type of multi-terminal networks. And we found that there are only 12 forbidden embedded networks for those more than 3,000 networks, as shown in the picture. So most of them actually are not scalar binary sufficient, and they can be boiled down to 12. And we will show the results again in the end of this talk. So after a broad view of this work, so we will enter into the details of this talk. So at first I will introduce some background on rate regions and linear codes, and then I will define the network operations, and then demonstrate using MDCS, which is a multi-level diversity coding system. Okay, first the background. So the networks we considered are multi-terminal networks, which are usually represented by directed acyclic graph, as shown here. There are multiple independent sources. Each source has some source rate, and output of a source is a function of the source variable. And we have possibly different capacities for each intermediate edge. For every intermediate node, the output is a function of the input. There are multiple sinks where each requires a subset of sources, and these subsets can be different. This region contains all possible rates or capacities and source entropy vectors satisfying all such network constraints. So if we collect all random variables and define the region of entropic vectors gamma and star, where entropic means there exists valid distribution associated with the joint entropies. And we can define the sites L1 to L5 corresponding to the network constraints we just mentioned. The Ritter region in terms of rates or capacities and source entropies can be expressed this way, which is derived from Yang and Zhang 2012 Trans-IT paper. We consider the sufficiency of linear codes. We know that for an intermediate node, the output is a linear function of input. This is called a local function. And if we recursively trace back, we can find the output is a linear function of sources, called the global function. We consider the global functions, and we know that in general, one variable may have multiple columns in the coding matrix. We denote the region achieved by such general codes as RQ. And there's also a special case where each variable only has at most one associated column in the coding matrix. So we denote the corresponding region as RSQ. So next I will show the network operations. First one is called source deletion. Source deletion is pretty simple. So when the source key in A is deleted to get the A prime, the source stops sending information to the network, which is equivalent to say HYK equal to 0. Of course, the sinks who require K will no longer demand it after the deletion of K. Then we have the relationship between Ritter regions of A and A prime. Ritter region of embedded network A prime is the Ritter region of A with the intersection of HYK equal to 0, as shown in the picture. The big Ritter region of A intersecting with HYK is the region for A prime, because if a point A prime is picked in the region of A prime, it is equivalent to say there exists another point R in the region of A such that HYK equal to 0, since all the other network constraints are not changed and are not affected. And if R is achieved by FQ codes, then the code to achieve R prime can be the same code with sending nothing on YK. And since it's sending nothing on YK, it's a valid, it's also a valid FQ code. So you can do both ways in the proof, so that we see that if A is FQ sufficient, A prime is also FQ sufficient. The second operation is edge deletion. Edge deletion is also simple. Similar as source deletion, when an edge E is deleted from A, nothing will be sent on E. It is equivalent to say the capacity of E and the entropy of UE is equal to 0. Then we have the relationship of Ritter regions. So the region of A prime is the region of A intersecting with RE equal to 0. As shown here, a point R prime in the region of A prime is equivalent to a point R in the region of A with RE equal to 0. So if R is achieved by FQ codes, then the code to achieve R prime will be the same code with the deleting columns for UE, because UE sending nothing on edge contains nothing, and contains nothing is also a valid FQ code. So you can do both ways. If you pick a point in the Q A prime and UE is sending nothing, so it's also a valid FQ code in the region of RQA. Similarly for the scalar case. So we see that the sufficiency of FQ codes are preserved under this operation. Our third operation is called edge contraction. It is similar with graph edge contraction. So we know that in graphs, when an edge is contracted, the two nodes it connects will be merged. Here, if two nodes are merged, all input of the tail node will be directly available to the head node. So which is equivalent to say the capacity on E is infinity, and you can send whatever you want on E, and HUE is free. Therefore, we just drop the dimension of RE in the region of A to get the region of A prime, since we are not interested in that dimension anymore. A point I prime in the region of A prime is equivalent to a point in the region of A with some HUE, but we just don't care. If R is achieved by FQ codes, the code to achieve R prime is the same code with the deletion of UE. Possibly UE send everything available to next node. It is different with edge deletion. In edge deletion, UE sends nothing, but here it can send everything. We just don't care about it. Hence, the relationship of scalar code for scalar codes only has this subset relationship, because if you pick a point R prime in scalar region of A prime, we are not sure if UE will use scalar codes for if UE will use scalar codes. So we don't have scalar construction for UE in A. But this subset relationship suffices to prove the preservation property. We see that if RSQA equal to RA, equation 13 and 15 indicate RA prime is a subset of RSQA prime. But we know that trivially RSQA prime is a subset of RA prime, because it only considers the scalar codes. So we have the equation of equation that RSQA prime equals RA prime. So the sufficiency is still preserved. So next I will use multi-level diversity encoding systems to demonstrate these operations and the results. So MDCS is a special class of multi-terminal networks. The sources are prioritized. Well, high priority means it has high priority at the decoders in the decoding process. So decoders are classified into levels, where a level K decoder must decode X1 to Xk. It does not consider intermediate nodes, and decoders have access to subsets of encoders. MDCS instances are usually sorted as represented as KE pairs, and the corresponding operations in MDCS. So the first one is source deletion. So here, if source Z is deleted, the decoder D5, which requires Z, will not demand Z after the deletion. Here, D2 and D5 will be the same after the deletion, so one of them can be deleted. Edge deletion corresponds to encoder deletion in MDCS. For example, here E4 is deleted. The decoder D5 will no longer have access to it after deletion. D2 is deleted because it is redundant after deletion, which it is implied by D5. Edge contraction corresponds to encoder contraction. Here, if E4 is contracted, all decoders connecting with it will directly have access to all sources, and all constraints are trivially satisfied. So these decoders will be deleted. Okay, we now have a look at the results again. So we as I said before, we consider the sufficiency of scalar binary codes for more than 7,000 networks with different KE pairs. And we see that among the 7,316 instances, only 1,922 instances are scalar binary sufficient, while more than 5,000 are insufficient. So the insufficient instances can be boiled down to only 12 forbidden embedded networks with the 3 operations we just defined. However, we don't have a complete list of forbidden embedded networks yet. Further, we don't know if the number of forbidden embedded networks for a field is finite or not, like Rota's conjecture. In matrix theory, we also don't know. We also need to understand how the topologies determine the insufficiency of linear codes, and these can be our future research directions. Okay, thank you. This is a reference, and thank you for your attention.